Hello everyone, our report provides an overview of security and scalability of blockchain. To facilitate the discussion, we first introduce the concept of blockchain and security and the privacy properties required by many blockchain applications, and then we will reveal the security and privacy technology that implement these security properties in blockchain-based systems, including imperative consensus algorithm and others. We hope that this report can help readers learn blockchain security and privacy, including concept, properties, and technology. We reviewed some related papers and found that technology has significantly advanced and improved in recent years. So our report focused on the advanced blockchain security and algorithm research in this year. Blockchain technology have key features such as decentralized, persistence, anonymity, and adaptability. With these features, blockchain can provide significant cost-saving and efficient gains. From a security perspective, blockchains are created and maintained using peer-to-peer online network and are protected by intelligent and decentralized use of cryptography and cloud computing. The security proposed of blockchain system from the advance of cryptography and the design and the implementation of Bitcoin. Built to ensure many security purposes, the blockchain in Bitcoin retains three security properties, including consistency, tamper resistance, and resistance to DOS attack. Consensus algorithm. Consensus in the context of the decentralized blockchain. When a new block is sent to the network via broadcast, each node has the option to add the block to copy the global ledger or ignore it. Consensus is used to seek agreement on individual state updates from a majority of network to ensure scan of the global blockchain and prevent dishonest attempts or malicious attacks.
In this section, we will discuss about a bunch of techniques that can be used to protect the security and privacy of blockchain systems. In our report, we studied 9 technologies related to blockchain security and privacy. The first one is mixing. Here, mixing services are designed to prevent users' addresses from being leaked. Relevant applications include Mixcoin and CoinJoin. The first generation of mixing services has used centralized servers. However, centralized services may have the risk of leakage of users' privacy. Anonymous signature provides anonymity for the signer. Anonymous signature has been used in several blockchain systems such as Platon, Cryptonote, and Ethereum, and so on. Homomorphic encryption is also used in Ethereum. It can be used to store data over blockchain, preserving privacy and security. However, the computational efficiency is a potential problem. Attribute-based encryption is another cryptographic method, although it has not yet been deployed in any form on a blockchain for real-time operation. Some decentralized ABE schemes were proposed to employ ABE on the blockchain. Multi-party computation allows multi-party to carry out some computation jointly over their private data inputs without violating their input privacy, and it has already been deployed on Enigma, which leverages an external blockchain as a corruption-resistant recording of events. The next one is non-interactive zero-knowledge proof. In the blockchain system, all account balances are encrypted and stored in the chain. When the user transfers money to another user, he can easily prove that he has sufficient balance for the transfer with zero-knowledge proofs without revealing the account balance. The Trusted Execution Environment (TEE) provides an isolated environment for application execution, preventing tampering from other entities. Based on TEE, the smart contracts can have privacy guarantees. And there is also a very recent development for smart contracts verification, which is game-based solution. As the name suggests, this scheme uses some game-like incentives mechanisms, some real applications in blockchain such as Truebit and Arbitrum. Through the research on these security techniques in blockchain, we have gained some insights. First, no single technology is a panacea for security and privacy of blockchain. In general, the combination of multiple technologies works more efficiently than using a single technology. Second, there is no perfect technology in all aspects. This requires careful attention on the potential harms induced from integrating some security and privacy techniques into the blockchains. Finally, there is always a trade-off between security, privacy, and efficiency. We should advocate those techniques that improve security and privacy of blockchain and at the same time have an acceptable performance.
Next, I will introduce the issue of the scalability of blockchain technology. Since its inception, blockchain has grown in popularity. Its decentralized has led it to being seen by many as best solution for future applications of financial services. However, many problems still limited the development of blockchain, among which is the scalability challenges of blockchain technology. The current Bitcoin system can process about 7 transactions per second, while the traditional payment system Visa can process about 1,700 system transactions per second. The huge performance difference creates difficulties for the practical application of blockchain. Two important features to measure the performance of blockchain systems are transaction throughput and transaction confirmation latency. Transaction throughput is the amount of time and block size required to determine a set transaction. Depending on the categories of blockchain, as the number of transactions increases, the block size will also increase, and more computing resources will be required. Transaction confirmation latency is the progression time required for a transaction to be transmitted across all nodes, which can consume significant network resources. Another difficulty in solving the blockchain scalability problem is the blockchain trauma. While some researchers point out that blockchain systems, decentralization, security, and scalability cannot be met at the same time, any blockchain network can only achieve 2 of the 3 key features. There are 2 main types of existing solutions to the blockchain scalability problem: on-chain, including consensus and sharding, and off-chain, including off-chain channels and sidechain. Bitcoin uses the POW consensus mechanism, where all participants need to participate in a calculation to generate a new block. When the communication is completed, a war faction is sent to the other blocks. This mechanism consumes a large number of computing resources. The POS mechanism is a new solution that makes the node with more concurrency the leader by voting, thus avoiding the complication of validation and improving the system's performance. Sharding is a traditional technique to divide the network in a blockchain into smaller networks, with each part of the network having its nodes. Different shards handle their transactions separately, which can improve the overall performance of the system and its ability to handle concurrent transactions. Payment channels are channels where some transactions in a blockchain system are moved off-chain to reduce the volume of transactions in the main chain, while increasing the transaction throughput of the entire system. Representative payment channel solutions include the Lightning Network and the Raiden Network. Sidechain is a new model that allows assets to be transferred between different blockchains and is sent with a special artifaction to prevent denial of service attacks and protect the user's assets. Existing scalability solutions for blockchain systems have improved the performance of blockchain systems to some extent, increasing the transaction throughput of the system and reducing transaction confirmation latency. However, none of the existing solutions address the inability of blockchain systems to combine decentralization, security, and scalability. Most solutions reduce the decentralization, which can come with new security risks. Here are our reference, and that's all. Thanks.